Hello, everyone. This is Alejandro García from IDIADA. And from those of you who don't know IDIADA, which you should, but for those of you who don't, we are an automotive engineering partner, which is focused on helping our clients to achieve excellence and to achieve their targets and their goals within the automotive industry. Development, R&D, and many different things. We are a company with more than 3,400 people worldwide, and with that workforce, along with some of the best state-of-the-art facilities, such as track testing, different latest rigs, and mainly the knowledge that we have acquired through the years. That what brings us here to make a question. So how can we further help our clients to achieve the very, very demanding targets that the market has right now, which is to provide better products in shorter times. So with this in mind, that's what the different virtual vehicles are born. So we'll be seeing today what is a digital twin, why do we need them, how we have generated the different vehicle models and the different virtual models that we have available, which are already embedded in VI-CarRealTime. We'll see how we validate those models and how to use them on VI-CarRealTime with a demonstration. So yeah, first things first. As I was saying, one of the main difficulties that we face in the market right now, and also in the automotive industry, but in many areas, is the need of doing things quick, fast, and but still keeping high levels of a performance of a high level products. So we asked a question some time ago. Why don't we get a vehicle, get a car, and we can make it virtual? So we have the facilities, we have everything to virtualize this vehicle. And then if we do so, and we make sure this is behaving as a physical vehicle, then that will make a huge step forward in development. Why? Because with that, we could have a baseline that we could use either to generate many different variants, like almost infinite variants in way shorter times than we would do with physical prototypes, or we can investigate and develop systems, components within our cars just completely virtually, or we can even use them as benchmarks for product developments that are ongoing. So that was the reason why we decided to generate our first digital twin in IDIADA, and why digital twins are more and more staying with us and are more and more seen in the different development phases and processes in the automotive industry. So a digital twin is simple. It's nothing but a twin of a physical vehicle. So it's kind of not a vehicle, it can be whatever, but in this case it's a vehicle and all its systems that represents a behavior pretty accurately. So that's why do we need this? Because as you can imagine, we're heading towards virtualization and zero prototypes and things like that. And just changing the spring or changing the damper or testing different weight distributions in about 30 to 40 seconds, maybe, that will make such a difference. So we decided, okay, we have the capabilities, let's go for it. And that's how we generated a strong methodology, already validated and providing very good results, so that we are able to generate on-demand vehicle models. So we have the knowledge and the tools to perform all the testing required in order to generate, correlate, and validate these models. And these can be run, and this is very important, these can be run offline, but also in driving simulators. So for example, in IDIADA, we have one of VA grade STIM 250 driving simulators, and the models were validated subjectively there, and they are available to be run in our driving simulator, as well as in any VA grade driving simulator. And each model has been extensively, as I said, validated against real data that we also generate in-house. So we had at that point generate the capability of generating vehicle models, but what we have built since then, ever since, is a database of these vehicles. So we built a database of these vehicles that can be purchased along with the different data that has been used in the validation process as well as in the generation. Those models are available in VI-CarRealTime. Although some formats can be supplied if requested on demand, depending on the model and the demand itself. And the list of available vehicles is growing up very quick. At the moment, we have quite some vehicles there, but for example, this year we are planning to do testing for modeling up to 20 vehicles, something like that, to keep increasing the database and keep generating these digital twins. So yeah, that's pretty much why do we need the models and what have we done with these models. But to start knowing a little bit more about them is how do we generate those models that we're talking about, those digital twins. So we have tested extensively many different systems and the car itself. In order to get these things, we need the KNC to be tested. We've done tire testing, powertrain testing, objective testing, components and body measurements. And all of this has been done in-house or with the help of some of our most trusted partners. So in order to give you an idea of how a digital twin looks like, or how every area of a digital twin looks like, let's start with for example, with the KNC. So we have a KNC rig at IDIADA, and in order to properly model the different kinematics and compliance maps and steering maps that are from which the model is composed, we need to do up to 55 to 60 different KNC tests. We have got the results from those tests, and we have processed those results with one of our in-house tools in order to generate the skeleton of the model in VI-CarRealTime. So what we get from here is characterize all the kinematics, all the compliances at different vertical positions of the wheels. We get characterized the steering kinematics, this part of the steering system, and also we add additional sensors to get things like the motion ratio and so on. So it's pretty much a very complete characterization of the whole kinematics and compliance, which, as I said, is one of the main parts or the main skeleton of the VI-CarRealTime model, the digital twin. Then these models, of course, need tires. And in terms of tires, all models that we generate are assembled with MF tire. Those MF tires have been generated in-house. We have state-of-the-art facilities, and such as the trailer that we can see here, but also some drums and static form measurement rigs. And with all that, we have a dedicated dedicated tire team, which builds this model, and we work together in the generation and validation of those tire models. F-tire is also possible. F-tire can be used with those models as well. It will be happening on demand in principle, but we have also capabilities to model F-tire in IDIADA. So apart from the tires, let's move on to the powertrain. So the powertrain is very simple yet complex. So we do all the testing in-house, and we do kind of a reverse engineering process to model the powertrain and the transmission. So we do some acceleration and deceleration tests. We do a sweep of tests with different sweep of pedal positions. So in that case, we can have the engine map, so the torque map, at different throttle applications. We can get the different shifting maps. So at the point where the transmission is shifting gears in case of an automatic transmission, we can also get the different gear ratios, and we can characterize a very simple yet powerful model of a complete track. So we can identify the drag coming from the powertrain, and then we can estimate which is the drag that will be coming from things like the aerodynamics or the rolling resistance of the tires themselves. Sorry. And I want now to highlight one of the most important points of the models, in my opinion. And this is because it's the only point that is connecting the driver to the digital or physical twin. It's the steering wheel. So most part of the feeling of the car on a driving simulator, for example, comes through the steering. And that's why it's very important to have a proper steering model. And for the different models that we have in the database that are now embedded in VI-CarRealTime, we do have extensively tested and correlated the steering systems. So the steering systems are mechanical systems. We kind of give them some baseline properties that we measure with the help of the KNC bench, and some based on our experience as well. And then we use all the data that we gather in testing at system, but also at objective, so full vehicle level, in order to validate two things: the mechanical system itself, different inertias, dampings, frictions, but also to generate a proper assistance map. So, for example, we'll see later how we use the objective data to do so, but we run a couple of steady state constant velocity tests at different speeds so that we can have a very accurate, we have different speeds to tune the assistance map on. So we can not only have 2 or 3 and interpolation, but we can easily control the whole steering assistance map and can provide the driver a good feedback of the vehicle. I think this is one of the key points, especially when talking about subjective assessment and usage of these models. But besides that, we also measure components and measure the body of the vehicle. So we sent the vehicle to one of our trusted partners to measure the complete inertia tensor and the center of gravity position. And also we measure the dampers, springs, everything, every component that's on the every force element of the suspension is detached if possible and measured in order to be as accurate as possible with the modeling. And finally, things such as the braking system is completely correlated offline with objective data. We use the different braking tests, straight line and intent braking tests, to refine some initially given parameters to the braking system, so that we can end up with a proper digital twin that behaves like a real car. But we don't want a model that behaves like a real car. We want a model that behaves like its physical twin. So how do we trust the model that we generate at this point? Well, this is an overview of how we correlate these models. We follow 3 steps. First, we validate the model at KNC level, so at system level. We validate both suspensions and the steering system in order to understand if the handling of the vehicle, every bit that might be deviated from proper correlation, it's not coming from the kinematics. So we use the KNC data to correlate the models, the front and rear suspensions, the steering system, and also to correlate things such as the steering mechanical stiffness and the frictions of the system itself, for example. Then we would jump to the offline correlation. So we get all the testing that we do to the vehicle on an initial phase, and we use this to correlate and validate every single test between the physical and the digital twin. And once we complete this phase, then we are ready to move to the driving simulator and perform the last step of the validation, which is with the help of a tuning engineer, of a subjective driver professional. We get his feedback, her feedback, and we finalize the tuning of the model so that we can make sure that everything has been extensively checked, and we go back to the offline and the KNC correlation to make sure that everything is aligned. And by that time, after those 3 steps, we are able to sign off the model and say that, yeah, this is a really good model. So you can see here in the bottom right corner, we have some examples of correlation. For example, a frequency response test, a step steer, and things like that. And correlation is pretty good. So we're quite happy with the models. And of course, there is some forth and back in this phase. It's not that we don't go back once we leave one phase, but we ask ourselves if the correlation level is good enough at some point. And if it's not, then we go back, we adjust some parameters, the ones that we don't measure, or even the ones that we measure, but we know they might have some small error or some error. For example, the tires, there's always some mismeasurement of the grip depending on the testing and things like that. And then it's kind of an iterative process that goes on until the driver, the engineers, and everyone is happy with the model, and we can say, okay, this is validated already. And at this point, as I said, those models are already available to be used in VI-CarRealTime. So to explain how to do so and the science behind the usage of those models, I think my colleague Francesco will take over now.
Thanks, Alejandro, and hello, everybody. I am Francesco Ambrogi from VI-Grade, and today I'm going to discuss how these models that Alejandro has introduced and explained are becoming available to potentially all VI-CarRealTime users. So for enabling this possibility, we're basically relied on a functionality that was already implemented in VI-CarRealTime since a few existing releases, with the possibility to protect a VI-CarRealTime model by obfuscating the content of the model data in a way that the intellectual property of the model is maintained to the proprietary individuals. Also, we wanted to provide a controlled distribution of the models so that the creators can, let's say, share securely to specific users and organization the content of the model. And in this way, it is also possible not to, let's say, provide sensitive information and data to anybody who is not supposed to receive it. In this context, what we have also done for release 2025.1 of VI-CarRealTime is to include a licensing control that, beside obfuscating the models, is also allowing to distribute them only to specific users that are in possess of the related simulation and modeling license. The models that are currently available are listed in this slide. So basically, we are starting from a set of 7 models that have been already prepared by IDIADA and validated from the objective and subjective point of view. So very quickly, we can go through the list of them. We will have the Mercedes EQS. So we are talking about an electric vehicle, first version of vehicle belonging to the platform MEA, and this is going to be released. As you can see from the table, we have also listed the level of correlation that has been reached, and what is instead indicated as representative means that not very deep testing has been performed to correlate, for example, ride or longitudinal dynamics, but according to the measurements that have been taken to the experience on the driving simulator, they can be considered as a representative of the overall vehicle performance. In this case, the model is also supporting specific controller for what regards the rear wheel steering that has also been included in the model that is going to be distributed. A different take of electric vehicle is also given providing the BMW iX3, which is belonging to the Neue Klasse vehicle platform. And also for this case, you can see the level of correlation that has been reached. In this case, we have no specific controllers that have been modeled. Again, another electric vehicle is Hyundai Ioniq 5. That is also an electric vehicle that has been characterized. And moving to the more traditional side of things, so the internal combustion engine models and vehicles, we have in the database the Kia Sorento, the Ford Focus, we have the Golf 8, and also the BMW Series 3. So this is a first, let's say, set of vehicle models that we have prepared. Of course, as Alejandro mentioned, additional vehicles are going to be measured along this year and in the following years. So we expect that the database will become, let's say, wider and covering more models. Okay, so that said about the model database composition. Let's talk a little bit about the usage of these models. As I mentioned before, the possibility of using in the VI-CarRealTime obfuscated models is being available since a few years. And in this context, basically, the data set that is typically used for a simulation, which is based on the so-called SEN SVM file, which is an XML file containing all model data, is basically split into two parts. So two different files are used for representing the model, the vehicle model. One part is completely obfuscated, so the data content is not accessible by the end user, and another part that is opening to the, let's say, replacement of a specific set of data or setting of the model is instead available for the user. So in this case, for example, the end user is allowed to modify some parameters like aerodynamic properties or type property data, or again, we can also mention the powertrain map data. These are all properties that could be, let's say, potentially used and changed by the end user. In addition to that, in VI-CarRealTime, we offer the capability called model parameters overlay, which is provided to an XML file, which is basically as the role of overlaying some data content which is included in the obfuscated part of the vehicle model. So in this case, the user can change more specifically some model parameters that are typically not accessible within the file, but that can be replaced with the user for any purpose, either benchmarking or for, let's say, addressing specific design design needs. This file can be generated from the VI-CarRealTime user interface, and basically can be used to define a variant of the model that is, first of all, loading the model content into the VI-CarRealTime environment, and then replacing a set of data specified by the end user with parameters that he can choose. So, and those parameters can be a full set of model data set, including, for example, again, the type properties or some suspension parameters. In general, a wide set, if not a complete, but wide set of the model parameters. In addition to that, it's also possible to provide through this override file some extension to the model that are related to the implementation of specific subsystems, like it could be, for example, a control system or a component that has been modeled in more detail. So just to make it a little bit more concrete, we wanted to show you now a demonstration of this functionality. So what you can see here is basically the typical VI-CarRealTime session. The models will be distributed in the typical shape of a VI-CarRealTime database. So the first thing that we need to do if we want to use it is to register the database in the session. From this point on, the model can be used for simulation. As we said, it's not possible to access directly the data, but we can use for the simulation. And what we do here, for example, is to take an event that has been generated using VI driver for, let's say, closed loop path and velocity profile following, and we just go in the model entry of the event by selecting the obfuscated model that has been provided as a model for the simulation. And this is mainly the only difference from a standard VI-CarRealTime model expressed as a single NES system file. But as you can see, we can then start the simulation and provide and then generate the results for it. So as soon as the simulation is complete, moving to VI-CarRealTime review mode, it is possible to load results into the post-processing application VI Animator. And here we can associate with the simulation results also a specific graphic model, so that in the animator it will be possible not only to see the, say, plots of the signals generated by the simulation, but also view an animation of the model. We can complement this setup, including also the graphical scenario. And from this point on, we can, for example, generate an animation of a movie of the specific event that has been run. And at the same time, we can access the simulation time histories or plots that are associated with simulation results. And so this is, let's say, how we can basically use the model out of the box. For example, if we want to compare the performance of one of these vehicles specifically with a vehicle that we are designing and studying at the moment. The next step could be instead to apply variants of the vehicle that has been provided. And as I mentioned before, the task for accessing the data set and providing generating a variant is to generate the vehicle override file, which can be done from a generic model in CarRealTime. So for example, in this case, I am selecting from the tree view of the model data some parameters that I want to override with respect to the originally provided obfuscated and licensed model file. So I selected the tire property files, taking them in this case just from a model that we have in VI-CarRealTime distribution. Again, we can do similar case by exporting another file with focus on, let's say, some other parameters, like could be, for example, anti-roll force scaling factor, so that we can also modify the activity on, in this case, of some components by scaling their effect in the simulation. So I am, in this case, generating an override file in which the, let's say, effect of the anti-roll bars is strongly removed, for example, to simulate a failure in the system. From this point, we can move into the simulation, and so what we can do is to implement again through a fingerprint a specific event. So I'm starting with a generic open loop ramp steer, and by creating a copy of this event, I'm basically preparing for running a simulation of my variant. As you can see, my model listed in the model field is my BMW 320 that I used for the previous simulation case. What I'm doing now is to select the override file. For example, in this case, I'm picking up the tire properties. And so what I'm going to simulate now is, first of all, the baseline simulation of the original model, and then I will be running the same simulation, same load case, but selecting a different set of tire properties. So at the end of the simulation, I can go again in review mode in VI-CarRealTime and fire up the eye animator to see the results comparisons for the simulation that I just ran. And here I'm loading the simulation results. Again, I can complement the animation with a virtual scenario, and then I'm able to review the results of these two cases that are exactly the same in terms of, say, driver input, but different for properties of the vehicle, in this case for the tire. So as you can see, there is a difference that we can enlighten also in the understeer gradient diagram that has been created in the last page of post-processing. Similar case from the procedure point of view could be to run another type of dynamic event, again a steering event, and we want to implement an impulse steer with steer release, considering two cases in which one is the baseline model and the second one is instead a model in which the anti-roll bar characteristics are being strongly reduced. So to simulate, as we mentioned before, for example, a damage in the subsystem. So again, the procedure is exactly the same. I select the override file for the suspension properties that I created before, and I can run the simulation. So also in this case, first I will simulate the baseline, and as a second step, I will run a simulation with the altered subsystem. So even if these properties are belonging to the obfuscated part, I have the possibility to apply change. And for that, I'm then going again in post-processing and loading the results. I can overlay the simulation and compare the dynamic response, again, in terms of visual animation or comparison of the system response, for example, in say lateral acceleration or side view angle, side slip angle of the vehicle model. Okay, so with it, we basically complete the demonstration of the tool. So to summarize what have been shown so far, we have the possibility of accessing this license protected obfuscated model. We have been talking already about the validation of them, the process of creating good quality digital twin. The distribution will be through VI-grade, who will be providing the model databases. As I showed before, it will be basically a single archive containing the asset for simulation and graphical visualization. And the procedure is, let's say, validated and certified by the IDIADA activities. And along with the model in the distribution, there will be also some documentation explaining the process of model creation, and for the specific vehicle model, also some reference data about the quality of the validation and specific diagrams showing, let's say, relevant validation results. The feature will be, and as it has already been released through the version 2025 of VI-grade software. Of course, VI-CarRealTime is just one of the pillars of the VI-grade solutions for simulation. And specifically, I just would like to complete this presentation just mentioning a few features that have been released with version 2025.1, which are very relevant and let's say that they are coupling very well with the functionality of providing validated vehicle models and digital twins. So for this release, the focus has been on creating models that have an enhanced external interface, providing a very high computational efficiency, implementing new features like the possibility of having save and restore support for Simulink models, which is also a portion of vehicle integration activities that the VI-CarRealTime vehicle model are used for. With this specific case, we have been working on creating a more robust interface towards MATLAB Simulink. As I said, also working on the efficiency of the simulation. So the typical case that we may have is a vehicle model which is supplied by a set of external subsystems implemented in Simulink. These subsystems are typically requiring some effort from the computational point of view. And you can see in this slide some metrics about the time that is taking for a typical simulation. So if we compare to tracks that are, let's say, relevant in terms of length, we can imagine that the simulation on the Calabugi track, which is 5 kilometers long, is about 4,200 seconds, while simulation on the longer notch life, which is the typical benchmark for several vehicle simulation, can last up to 35,000 seconds. So typically it is a task that is very, very time consuming, at least was until this release. What we have been done is basically to work on the possibility of exporting the content, the controller content of the model, and convert in a kind of standalone auxiliary plugin or library that can be used directly into VI-CarRealTime user interface. And beside to that, we have been also working on some improvement of the models, the model interface, so that the so-called save and restore that is needed, for example, for the max performance simulation, is now completely supported in VI-CarRealTime simulation. The result of this enhancement is basically that the model can be run completely independently for MATLAB after the export of the plugin, and the time needed for simulation is strongly reduced. As you can see, the simulation are from 15 to 30 times faster than the embedded simulation in MATLAB Simulink. So this is a nice improvement that we feel will be very much appreciated by our community of users. And in addition to that, we have also been working on other improvement, like the support of version 2 of FMU, which is now implemented and available in VI-CarRealTime. So this is also possibility of opening up the content of VI-CarRealTime to, let's say, external modeling feature that could be specifically applied also in the case of developing specific subsystems, also controlled ones on the obfuscated model that we have been talking about today. Okay, so this is basically it. Just going to conclude this presentation. Wanted to remind you that it's possible to receive additional information about VI-CarRealTime, and specifically about the validated vehicle models by scanning the QR codes in this slide. And so you can request a demo, and we can get in touch to discuss about additional details that you may want to know about these new functionalities. And with that, I thank you all for attending the webinar, and yes, we are available for any questions if you have it.
Thank you very much.